So now we need to talk about exactly what is a process or a task. And so POSIX defines processes and threads, and FreeRTOS calls them tasks. They're all really the same thing. Even in Linux, processes and threads are very much the same thing. And so these words get generally used interchangeably. The most common use of process is sort of like the whole program, if you will. For instance, writing these lecture notes, I use the program TextMaker. And if we look at, if I just looked for the process or the program running on my computer, we'll see here my username and the program itself, like what the program that was invoked, namely TextMaker. Now, this is the sort of, if you will, the main. This is probably the entry point to the program, the key core process. As you can see here, this is this process ID, and this is where the program's code lives. But from the program's code might actually generate multiple threads to do things in concurrently or do things in parallel. And so this is what it means here. When it's composed of multiple threads, the program itself is actually being executed using multiple threads on the system, and we can see them all here. There's 5 of them, and so this is really common in today's sort of software because our processors aren't really getting much faster. The gigahertz, the clock rates are not getting much faster, so we're really having to find other methods to increase the computational speed and power of our computers. And so we're finding a lot more cores on our CPU dies, and software is now being optimized heavily for multi-threading and parallel processing. So then, to go into what a thread is really, if you have a process here as the instance of a computer program, a thread is sort of like the smallest sequence of code, right? So if my program TextMaker is the process, then the threads are sort of like the individual pieces of work that need to get done to make the program run. And so the scheduling or the running of these threads on my system, on my laptop, is handled by the scheduler inside of the Linux kernel, since I'm on a Linux system. And so this allows for the program to be broken up into smaller chunks of work, because the scheduler makes sure that they all get done at the right time or in the right order or what have you, so that all the work gets done and none of it gets neglected. So there's a couple of sort of things that we need to go through, and one of them is there's sort of 2 concepts when it comes to threading, and one of the most important concepts is sort of like this concurrent execution. And so here, by the definition, a concurrent system is where you can split up execution of some work into multiple threads, and they can run independent of each other. So the output of one thread is not necessarily dependent on the output of another one. And so this is sort of like how your computer can run multiple programs. While sometimes there are dependencies, mostly in these sort of threads, and we'll get to sort of the other when they are dependent on each other. But on our program, my PDF viewer and my network management program, they're not dependent on each other in any way. And so you can say that they run concurrently on my system. They might share some resources, like maybe, for instance, my PDF viewer is writing to my screen. If I have my network manager open, it's also writing to my screen. And there's somewhere in there probably some shared resource they're both trying to get access of. But really how this is handled is very much dependent on the operating system. And so Linux itself, as I was mentioning before, doesn't really differentiate between processes and threads. The only real difference is that the shared resources are managed differently between processes and threads. They're really all the same thing. The scheduler treats them all the same, right? So the POSIX thread library, known as pthread library, is generally what you use on a Unix-based system to instantiate a thread in your program. So if you want to write a C program and to put a loop inside of a thread, we could use pthread create, and this would actually put that loop, that chunk of code, inside of a thread so that it can run concurrently to the rest of the code, right? And so this obviously gives us the advantage that if we have this much work to be done, we can split it up into chunks, if this is possible, and run them concurrently or in parallel, right? So this is sort of more commonly said as parallel. For instance, if you need to process an image, instead of processing the pixels like line by line by line by line, which can take a long time, we could, for instance, chop it up and run on each core, process, like, if we have 4 cores, we'll process 4 pixels at a time, each pixel on a separate core. And so this is parallel execution, which I think we'll get to in a little bit. But essentially, the biggest advantage of threads is that it abstracts away a lot of the the logic of your program's execution into sort of little chunks that you can then enable and disable. And so you can sort of break up either the modules of your program or the work that needs to get done into different threads, and then you just have to think about managing these threads and communicating between them. So a good example of it is, for instance, a single-threaded program here that we need to get some input or output from somewhere, right? A single-threaded process would come down and it would say, okay, cool. It would, for instance, open a file, and it would have the open call. And until the kernel returns the open, the actual file, it will wait for this function to return. And so if you had some large I/O call that really took seconds, your program would freeze because the single thread of execution has stopped. Whereas if you were to split this up into multiple threads, like one thread that actually renders the program's interface and one that handles the opening of the file, while one thread is blocked on opening the file, the other one that's rendering the interface is still running, and so your interface is not frozen, it still looks normal, right? And so this is one sort of advantage, is that you can get this, you can improve your responsiveness, but also you've modularized your code in that you've put the code for opening the I/O into one thread and the UI into another thread. And so the more experience you get with developing programs, the more you'll understand that really well segmented and modularized code is much easier to develop, and more so it's easy to maintain, right? This can also, though, lead to improvements in execution speed, sort of like as I was saying with this picture. If we can parallelize the execution of some data processing, then we increase the speed by some factor, some large factor. I mean, when it comes to GPUs and image processing, you can have magnitudes of speed increases, right? So then it can also help us to get better system utilization, meaning that if we split up all the work that needs to get done into tasks, the scheduler can make sure that the CPU is kept busy with any task as much as possible, right? And so when one task in this I/O example is blocking and waiting for something to read from disk, the other task that would be, for instance, responsible for reading in network traffic can run. And so while we're waiting for the hardware, like the disk, the hard drive, which is relatively slow to respond with the data we want, the network can keep doing its thing, and therefore we're getting better system utilization, right? The parallelization is sort of the other one I wanted to mention, and this is a little bit different to when we talk about concurrency, because concurrency is when a system, when sort of there's multiple threads performing, it could be part of a program, but there's multiple threads running on the same system at the same time. But parallelization is really taking some work and splitting it into subtasks that can be run in parallel. And so this is a very easy and predominant area that this is getting used in, is image processing, because for the most part images can be processed on a pixel by pixel, and therefore they're not dependent on their other pixels, and then you can just split it up, right? But then we get to this sort of multitasking and multithreading, sort of the definitions of the two, because these words get used a lot and interchangeably sometimes, and sometimes actually not in the correct way. So then we have this multi-threading, and we're talking about the division of a program into small chunks, and whether this be the disk I/O, the drawing of the UI, and the network. These are different sorts of types of work that we have then divided up into separate threads or tasks. And this multi-threading is allowing us to take this work and split it up into threads, right? And so actually taking one program's code and being able to segment it into logical threads. But multiprocessing, on the other hand, is actually a property of hardware, of like the CPUs, GPUs, accelerators that you find. And what this means is that it means that you have more than one CPU core, so that you can actually have parallel processing of threads, meaning that the exact same instance in time, the CPU has the capabilities to run 2 threads at the same time, right? And so then we have this and so that's what multiprocessing is. And then we have this problem now, and this is what a lot of my students at TUM have, is that they get given single core boards, and I'm telling them to make a multi-threading program. And so they're like, hey, but if I don't have a multiprocessing hardware, how do I do multi-threading? And so then this is where we come to context switching. And so what context switching is really the core concept behind everything that enables multi-threading when given a multiprocessing or even not a multiprocessing hardware platform, right? So to understand sort of how context switching works, which we'll get to in a second, we sort of need to know that the task has different states that it can be in. And this is, for instance, how the states that FreeRTOS has, and also the API calls or the function calls that you need to make in FreeRTOS to actually move a task from one state to the other. These tasks, like whether they have the same name or not, like for instance in Linux, suspended would be called sleeping. These tasks or these 4 states are generally pretty common in the computer science world. Running is generally running. I mean, that's also makes sense. This usually means that the thread itself is executing on a CPU. Ready means that it is waiting to get run on a CPU, and when the scheduler has decided, okay, yes, this task should run, then it will get scheduled into the CPU. Blocked means that it's waiting for something. So this could be disk I/O for another task, any sort of wait. It means that it's not being scheduled. It's not suspended, but it's currently waiting for some event before it can be rescheduled onto the CPU. So suspended, on the other hand, means that the task itself has actually been sort of put out of the scope of the scheduler, and the scheduler is no longer interested in it until it is then made ready again. So when we block a task, if we want to suspend, for instance, we go to suspend, and if we wanted to get scheduled onto the CPU, meaning the running here, this is the state where the task is running on the CPU, we then resume it using vtask respond in the FreeRTOS API, put it into the ready state where the scheduler can decide if it should be run. So we know that now we have like and for instance, running and going to block, this doesn't necessarily mean that the thread has been stopped, like finished completion, but it sort of shows that we can take a thread and take it on and off of the CPU. And so this is when we come back to context switching and how we achieve multi-threading. And a good example of doing this is to show how we actually achieve multi-threading on a single core. And so context switching is this taking of one thread that is running on the CPU and taking it off of the CPU and putting another one on. And so we'll go through in a second like the more details of it, but you just need to know that the context is essentially the state of the CPU's execution at some moment, generally with it's executing some code that's related to some thread, and we switch this to the code relating to another thread, right? And so these two figures here, they show essentially what we see as, let's say, very slow humans when I'm playing my little computer game. It's probably some multi-threading program, but it appears to, and if it's on a single core, it appears to me that everything is running in parallel, right? They're all executing at the same time. But what is actually happening is that the tasks are getting scheduled onto the single core that we have very quickly by the scheduler, so they all actually only ever one task has control of the CPU, but it does all of the work that we need in a pseudo-parallel fashion. And so this is what these figures show, in that this is what it appears like to sort of us as very slow humans that don't operate on a nanosecond sort of time horizon. And then we have here what is actually happening on the CPU. This is sort of really quick swapping of tasks on and off of the CPU. And if you have more processors, then obviously you have sort of one of these per processor, and then you have also the problem that you can switch context, you switch tasks between CPUs, and it becomes a very complex problem. So then if we look at sort of